Yeah, so we'll start from 4:10. I'll just enable mic access for all the participants and we'll wait if few wants to join and thereafter we can continue. Till then, if you have questions from the last week and the assignments that we solved that time, you can always let me know because this is like just free time now, waiting for more participants. And if people doesn't join, then we'll continue with this week's content. Okay, so let's start with this week. So, welcome everyone. This is like week two. I have given mic access to all who have joined. Yeah, so this week, last week we only completed like two modalities. And okay, so first my introductions. I'm Jagriti. I'm from IIT Gandhinagar, fourth year PhD scholar here, and I'm TAing for Professor Devdutt Sheth from IIT Kharagpur for this course that's medical image analysis. Yeah, so last week we touched on two modalities. First, starting from X-ray, CT, then instrumentation basics, how principal physics there goes into, and then followed by few of the applications of the fields, imaging modalities. Now this week, just as we thought, and last time, many of us also had some problems with that of how MRI, this T1, T2 weighted images, and those were coming up. So this week is like as discussed, we'll first go through uh, those basics a little bit into it, and there so first MR, then followed by ultrasound, and then I'll go through basics of image-based segmentation approaches, and the first one that we had in lecture slides. So which was it? I forgot its name. Yeah, so there were like this texture, and then we'll do segmentation. Okay, so I have some enough content for today. So I don't know how much time will we get for the assignments. So at any point, if we feel that okay, if that's too much of theory, then we'll shift to assignment because this week I've noticed that assignments are also like to be solved in a very conventional manner, how they do the textbook rule, and you don't have some tricky ways to solve it anymore. And some of the questions are too much into theoretical, so you need to understand the like you need to see the last three, four lectures briefly, or else you might also have to look into extra slide contents, like Google it yourselves like that. So that's for assignment, and the assignment questions are like from last week's are like 20 questions each. So we'll give like 30 minutes for that session proper time so that you'll be able to have a proper idea how to solve this assignment, which is like due in few days. When is it due? Let's see. Yeah, so this assignment, which is due by 4th March. So, yeah, you have enough time to solve it. And few of the questions are like more or less similar to the assignment questions that we do have. Also, following the last week's assignment that we said that proton spin for an hydrogen atom. So, the question there was, spins for an hydrogen atom. So, that was an atom, hence, it would be both electron and proton. However, I was confused that since the question had it as ion, so it would be just a proton. But if it's an atom, there are both. If it's just an ion, since it's positively charged, so it would be a proton spin. Okay. So starting with this week's lecture, we'll go with like I've only touched upon few topics that are very important in here, and I'm not going into that much depth. So wherever you want to go into depth, just unmute yourself and speak freely. Yeah, so magnetism and MRI, everything there works on this proton spins, okay? And this proton spins are nothing but we are particularly talking about hydrogen here. So, you know how electron revolves around nucleus. Now, whenever this electron moves around nucleus, or sorry, around an atom, in this particular atom we need something so that our all laws of motions and masses are being conserved, right? So there is nothing but our positive charge inside, which is nothing but in the nucleus, and this nucleus, it moves in the other direction. So okay, so now this moves in the other direction so that it will help us compensate for the angular moment. Angular momentum is then conserved. Now, momentum is nothing but product of mass and velocity, how it's moving through. But now we all know that mass of electron is very much smaller than that of mass of nucleus. Like nucleus is a heavy atom, a heavy substance there. So not an atom because atom has everything there. So now this in a way will be able to compensate for the higher speed of the electron that's been moving and the mass for the nucleus and electron that we have in this case. Now, suppose on like if you have like applied an external magnetic field in this direction. So now you might have studied something about dipoles and dipole-dipole interaction. Everything will be arranged into the manner where your magnetic field is being applied to. Okay, so in this case, the magnetic field is like applied in this axis. They will align. Sorry, 2 minutes. I need to take this. Sorry for the interruption. Yeah, so where were we? We were on this magnetism. Yeah. So whenever this external magnetic field is being applied here, this protons will either align parallelly or anti-parallelly there. Okay. And due to because of they are now, of course, they are being aligned because of this direction that they have, but because of this motion that they were being having, like they were revolving around each other, that frequency now resonates with this particular magnetic field this frequency, and how they are related are by the spinning or how they are spinning across its axis. So that is given by this gyromagnetic ratio and the magnetic field that they have, and this is your Lymer frequency. Now this frequency and how it rotates in a particular axis is nothing but it's related to this your external magnetic field. Okay, so that's a like a very basic relationship that you have whenever you start studying. So this is Larmor frequency, and this is your gyromagnetic ratio, and that's your magnetic field. Okay, now everything, since it's based on hydrogen, so the energy here is also lesser. It's like 40 to 50 megahertz in terms, so you can always go and relate it to respect to your one like unit Tesla, but consider in mind that Tesla is also a very big quantity. So how we talk it on Earth, it's everything, it's based on Gauss. Okay, so since now you might be able to relate from Gauss to Tesla, they have an order of 10 raised to power 4 relationship. Okay, now, this was a point where we were confused that why T1 and T2 weighted images look different, and what was the reason behind that. So we looked at one was a spin lattice, another was a spin. One took less time, one took more time, but why, and why the time gave us a higher energy differences, lower energy differences whenever we are looking at different tissue organs. Okay. So the basic principle behind it lies is the spin echo sequence. Now what happens in here, so I'll just give you a basic about the axis, or where the axis you should now focus it at. Okay. So if you have this, now usually you consider this as XY axis, but now since here in terms of MR, the pixels that we are looking at isn't only dependent on this XY axis, but we also do have an information about the depth across it. So now it becomes a volumetric pixel. So that's it, nothing but it's called as a voxel that we looked. Okay. Now for this voxel, delete the other parts. So I have something as this. Now this is my, or you can consider this as my XY plane, and this is my Z plane. So this particular plane is my longitudinal plane. Okay. Um, and this entire XY is my transverse plane. Okay. And in terms of MRI, whenever we do apply magnetic field, it's always in terms of this Z direction. So my magnetism, sorry. So my magnetic field is aligned initially towards the z-axis. So it is represented as mz. So that is my longitudinal magnetization. However, in cases when it is, or when it is being done, we'll look at it later. But when it is done, we'll be looking at this particular xy domain. So that is your transverse magnetization, and that is nothing but mxy. Okay. We also looked at there were T1 and T2 specific sequences. 2 minutes. Sorry. Yes, here. Someone was trying to say anything. Okay, I hope not. Okay, so here, sorry, sorry, what? I am writing here. Okay. Are you not able to see my tablet version? Are you able to see this part?
Yeah, it's visible.
Okay. Yeah. Yes, so the one which is along z-axis is the longitudinal magnetization. The other one is your transverse magnetization. Okay. And then you have T1, T2, then you have time of relaxation, you have time of echo. So you have this 4 variables till now. Okay. This is time of relaxation, time of echo, and then you have your T1 weighted images and you have T2 weighted images. Okay. Based on this relaxations only, based on these 2 times, you will have everything occurring in there. So for basics, this is nothing but your spin lattice. Now this lattice in this case is your tissue microenvironment or your tissue environment. Okay, the environment that is interacting it with, and this is spin. Now, where and in which axis it is being done, that is something important you need to consider. Okay. Now, at time t equals to 0, everything is at everything is like in this particular domain. Now, what we are trying to do in this case is we are trying to give it an excitation. So we are giving it a RF pulse, a radio frequency pulse, which is nothing but in this particular axis, this 90-degree axis. So we are giving it a 90-degree pulse to it. Now this 90-degree pulse will shift all of the dipoles or electrons which are like in this transverse domain. Now they'll be shifted back to this axis. So making a 90-degree angle with this axis. So now we have everything mapped in this Z direction. So everything in this case now becomes in here. So hence it makes your first mz as maximum, mxy as 0. Okay. Now when you have this particular case that now all are being gone to this, sorry, where did it go? Yes, that your mz is maximum and your, did I confuse it? Sorry. Sorry, what was your initial condition? Your initial condition is that your magnetism is aligned to the z-axis. Okay, so in that case, these are your conditions that mz is maximum. Let's write it here. Your mz is maximum and your mxy 0. Then you apply a 90-degree pulse here. So this 90-degree pulse is being applied. When you apply this 90-degree pulse, what happens is now your magnetism, everything which was here, now it gets shifted to this plane because of your shift. Now, all you have your protons which are aligned in this XY axis. So because of that, it won't be a sudden change, but what you see eventually is that your mz becomes 0 and your mxy becomes maximum. Okay, that's what happens. Now, when it is in this particular case, it is a like it's an intermediate stage for it. So, not everything. It's not a stable. Yeah, it's not a stable state for all the electrons to lie into it because your magnetism is being applied to this particular direction. It's continuously being applied. So you are not like gradiently changing it after one point or another point. So now, since it was shifted to this point, now all your electrons will start losing their energy because we gave it an energy of 90-degree pulse. They all shifted from their lower state of energy to higher state of energy. And now since that energy is being lost because that was just a sudden pulse that you gave, now air relaxation begins from that. Okay, now they'll all start releasing energy. Now this energy release can be in the form of heat, can be due to their collapse, can be due to some state variations from one atomic shell to another atomic shell. Now what's happening is they are trying to relax there. Now when this is being relaxed, now we were in the transverse axis, in this particular axis, and the stable state, the initial state from them for there is nothing but the z-axis. So all of them will inherently naturally try and occur to go to that particular point. So they'll try to recover themselves. Now when they try to do that, we call that process as T1 relaxation. And this relaxation is nothing but recovery of all those ones which lost their energy to its maximum state where they were previously. So recovery of this magnetization, the longitudinal magnetization that you had with respect to the tissue microenvironment. So what happens in that case is, so something as capacitor charging effect. So now they'll all be relaxed, they'll try to recover till like 68% of their energy. Now when this happens, there's a simultaneous effect which is being occurring. So that is nothing but your this axis. So now since they are trying to recover in this axis, what is occur is like simultaneously or consecutively being done is they are decaying in this particular domain. So the decay in that domain is being considered as T2 relaxation. It's not relaxation, but yeah, that's how you write it as, but it's a decay. And the process it's being called it as free induction decay. Okay, now when they are trying to relax there, so for them to relax only does it mean is for them to decay in that axis. So for them, it would be a exponential decay, similar to as that of capacitor discharging effect. And this discharging effect will lead to as something as 37% of loss of energy of them in that particular axis there. Okay, now when this effect is being occurred, now, how do you like compare it? Okay, so this was your T1 relaxation, how it was being recovering there. So now this energy, for it to make maximum towards our initial magnetic field where it was being applied, they'll have to resonate with the Raman frequency that we had initially. So they'll have to match it with the Lama frequency, and that means that the shorter the time it takes to recover, the faster it will resonate or match it with our Lama frequency. So hence it recovers quickly, right? So the ones which are shorter and taking lesser time to recover, in those cases here, they'll appear brighter. Okay. So tissues which have a shorter T1 will appear brighter, which is like they were as bones and other ones, whereas not as that of CSF and liquids there or gray or white matter who have a longer time. So that those times and how much time it takes in terms of milliseconds, that slide is there in lecture slide, so you can go and visit it. So the goal here is how it matches it. If it's shorter and quickly recovers, that means that it is brighter in that case. However, it takes a longer time, then after that it will saturate, as in this phase, this particular phase that you have in here. Okay. However, other way is your T2 relaxation. Now for your T2 relaxation is nothing but now all of the protons and electrons which were like aligned in one particular axis or your dimension. Now they are all suddenly trying to lose the energy that they had. Now what are they losing here? They are losing the phase that they had with each other. So the phase coherence is being lost. So that's decreasing or it's being lost. Now, as quickly it's being decreasing. So the sensitivity of our instrument to detect that signal when it losses to about like 37% of this is the time when we get our echo. Okay. So the longer the time it takes, so it's better for us because we'll get signal till that time, and hence the ones which have like higher T2 signal will appear brighter. Okay. So there's like so hence always T2 takes times to recover. T1 takes times to recover, whereas T2 takes times to decay. So there's like this simple rule that T1 is always greater than T2 because it takes more time to relax, whereas T2 takes lesser time to decay. But we want T2 to be larger so that will our instrument is sensitive enough so that we can detect the signal and measure it at that particular time of time. Okay. Now, what is this 180-degree pulse here? Now, this 180-degree pulse here was nothing but was the pulse which was being applied so that we have everything in this particular axis again. Okay. Now, since this 90-degree was applied, now they all are here. Again, 180 degrees applied because they all achieve here because they themselves have a natural tendency to go and align with the inherent magnetic field which is being applied to. But this is like a conventional form of spin echo and which is like not at all preferred because you don't want the patient to be constantly under magnetic field. Of course, magnetism does not cause you anything or it's like non-ionizing form of radiation, but it's not good for our body, for our cells to go through this constant 1 Tesla of magnetic field that's throughout our body. So what they then came up with that a gradient magnetic field. So you'll have different coils, but your entire body will appear like will go through a gradient of a Tesla of magnetic field instead all organs at a time. So then you'll get slices of frequencies at each and particular, let's say I'm trying to image my neck or this coil or trying to image my shoulder. So both of them will have different slices and the tissues there, the scattering that I'm getting through there will match up to a different Lama frequency. So that's how then they'll be trying to see that, okay, how your Lama frequency matches up, then how your T1 changes and how your T2 changes at that time. Okay, now TR in this case was the time of repetition. So how much time it takes us to get like from one 180-degree pulse to another 180-degree pulse, and TE is the time of echo, is like the signal that you get when T2 decays. So from here, it is like intuitive that T1 weighted images are dependent on the time of relaxation or the time of repetition of this 180-degree pulses, whereas T2 weighted images are nothing but dependent on this time of echo, the time where we get the signal at. Okay, so following it, we have like a table that if you have a T1 weighted images, you have a T2 weighted images. There's another the special category, but it wasn't discussed in brief. But I'll just write it here. It's something as proton density weighted image. Okay, so then if you have like, let's say your time of repetition, you have your time of echo, and then which effect dominates here? So what do you get? Okay, so I'll just ask you guys to tell me the effect. So if I have a shorter T1 and I also have a shorter time to echo, which effect do I get? Do I get a T1 weighted image or a T1 recovery or T2 decay? On this proton density is something different, but for now, let's just focus on T1 and T2. Which effect do we get here? Yeah, so if one is shorter, if you get a recovery fastly, that means that what is dominating there is T1 weighted image. Okay, so you have faster recovery there. Now, the other is if you have a longer time to repetition and you again get a longer time to echo, so it's not decaying quickly, you're getting a far enough time, so it's like a longer enough time to measure the signal there. So that is something as T2 decay. So in that case, you'll get a T1, T2. But if you use both combinations, so if you use a shorter time of repetition and a longer time to echo, you get something that is called as a proton density image. So you don't need to focus on it, but this is also part of the basics and you also get to know about into it. So it's like something which is after these two, but regular images do not use it, but just for mentioning it, I just added it here. So if is this clear till this point, that now are you clear why CSF that day was more brighter for T2 and not for T1? Is this clear till this point?
Yes, ma'am.
Okay. Now, next was ultrasound imaging. Here, the schematic was like we had different phases. But what is ultrasound? Ultrasound is nothing but a mechanical wave, and this mechanical wave has different. It's like a regions. So one region for them can be a compressional region. So if you see in this case, the other region can be a rarefactional cases where they are like far apart from each other. So you might see ultrasound as a wave. So whenever you go to cricket to watch cricket in a stadium, something nice happens there. If someone shoots a six there, so you see people jump and they stand and then try clapping. Now everything there propagates in a way like now the ones which are like watching closely will get a reaction faster, and then the other one. That's why stadiums are like formed in a way that it's circular and everyone will have like a equal way of moving. So it's nothing but a red eye kind of thing from the center where the pitch is being going on. Okay, so ultrasound is a mechanical wave where you have disturbances. Because of those disturbances, the particles will move. And ultrasound does need a medium to propagate. It cannot propagate in air. So, no, sorry, cannot propagate in vacuum there. Okay, so yeah, so what happens is if you send signals, so what are like these frequencies of ultrasounds? You have these frequencies which are beyond our audible frequency. So something that you cannot listen. And the frequency range, conventional imaging frequency ranges lie from let's say 10 to 20 megahertz max. And the ones which are like higher from there are nothing, not lying into medical ultrasound regions, whereas they do fall in between clinical or research based ultrasound. So this is the range which follows, that we have this clinical imaging as 2 to 20 or 15 megahertz max, and then followed by it's like small animal imaging, which is not at all into clinics yet. That is like for further research which can be implemented in future. And then you have therapeutic ultrasound. So that is, if you know, as physiotherapy, if you might have gone, so that using heat to release tension in between your muscles and tissue. So that is also a part of ultrasound. So here, using this one particular approach, you can not only see inside human body, but you can also provide drug to the different organs where you want, can do drug delivery in cases of cancer, those parts. So that's something as advanced part, but here we are looking into it's more of as an diagnostic modality. Okay, so this is how a conventional ultrasound imaging system looks like, this one. And what you're looking here is nothing but a linear array transducer. Now transducer, this term you might know that it is something to sense it. Okay, to sense energy. And these transducers do have something which is called as piezoelectric crystals. Okay, and what are these piezoelectric crystals? These are nothing but they are used to convert one form of energy to another form of energy. Okay, so at cases where you are like powering up the system, so what you are doing is nothing but do you have electrical energy, then this transducer will have a piezo crystal therein. Of course, you'll have like damping layer, backing layer, you'll have a crystal, you'll have a lens now to converge the energy at one point, but just at like pure basics, you'll have a transducer here. This transducer, when it and a piezoelectric crystal in it, when you have electric energy going around, it will convert that electrical to mechanical. Now, when you go send this mechanical energy inside your body organs, we all have different tissues, cells, and the smaller forms of it. So when the sound wave interacts with them, you'll get different scattering from it, and this scattering won't at all come at all same time. So they come at each of them will take its own time to come back to our system or to our body, to this particular sensor that we are sensing it from. So now when it comes back, we'll use it as a form so that we can take this all echo patterns and get an idea about the structural information of our inside body. So all the scatters that you have, so sound scatters this tissues very differently. So not all tissues will be scattered in the same manner. So it would only be the case where you'll have a homogeneous tissue, and that homogeneous tissue is always an approximation to just begin with, but it's not the case because tissue has different varied amount of heterogeneity there. So this is how it comes that, okay, you have a transducer, within it you have this piezoelectric crystal in between. So this type of crystals are nothing but something as quartz, then you have something as PVDF, then PVDF is polyvinyl difluoride, then you have something as lead zirconate, titanate. So you have like different types of crystals, and nowadays people are also doing it using this polymer based films. They are doing something as CMUTs. So then you have this PMUT. So there are like different parts of it. It's like a whole base fabrication, micro processing based field. So that's a different part of it. It's into materials and electrical electronics part. But yeah, so what happens in here that when you send a pulse, you have a tissue of interest, you'll have different body organs, different pathology there. It will reflect it back, and through that, in this particular transducer is nothing but something which will be sensing it also and receiving it also. Okay, so now it is sending it and sending the energy, also sensing it back, so receiving it here. And both these forms are nothing but towards the end. Here, the piezo's which are being inserted into this ones are like helping us to convert this one form of energy to another. So towards the end, you get this electrical signals. Now, when you have those electrical signals, those signals are nothing but something as uh, voltage varying time pulse. So, or you can also call it as amplitude varying time pulse. So this pulse can be something as this. Now, when you get it through one element, it is called as amplitude based signal. Okay. When you get it through this entire array and then you club it all together, you will get like if you have n number of elements, let's say 128 elements. So for hardware complexity, we keep it like as 2 raised to n power of elements, and then you'll get multiple this n number of lines. When you stack them all together, you get a 2D matrix, right? This 2D matrix will show you that the rows across which the depth that your signal has traveled, whereas this one is nothing but your this transducer elements. So how much? So this is your one A line that you are plotting all together. This, when you complete signal processing there, gives you this particular image. This is nothing but called as B mode image. So that is nothing but brightness mode image. The information that this type of image gives you is nothing but using this single lines, you only had information about 1D data. That's nothing but across rows. Now here, when you club all of them together, you get the whole some tissue-based level information. So here it was just a local data, whereas here it makes you a global information about your tissue of region of interest that you're trying to image. Okay. So that's how you club them all together, and here's a nice schematic into it. So if you get signal through one line, this is the echo that you get at different pixel level. So that's a A line ultrasound. So that is also called as A mode ultrasound. Then it's like when you accumulate it all together across all your transducer array elements here, this is how you get a B mode ultrasound image. And like you might have different structures around your animal, so that is how the echoes that you are receiving back are also changing. Now when you get this echoes all of similar intensity level, and you might want to send signal equally to all tissue parts and all, that is something this hardware incorporates it into, so we don't need to go into it. Then there are different modes of ultrasound. So one is Doppler. That's nothing but motions. You might have heard about Doppler ultrasound, where you that is something which is related to the frequency of the or the speed of sound. So how much the speed of sound vibrating in a direction and how much it is varying with respect to the medium. So since we talked about speed of sound here, can any one of you tell me that what does the speed of sound in a medium depend on? So we can call it as proportional, or what is it function of? So you might have heard about speed of sound in your early classes also. That
Yeah,
how is speed of sound?
sound attenuation or acoustic impedance.
Yeah, but I'm just asking on like very basics. So it's like a
The
function of
particle density
density.
maybe.
Yeah. And then what else?
Nah, I
It's
can
bulk
remember that's
modulus.
it. Yeah. Sorry.
Bulk modulus.
Okay.
Yeah. So one is the density of the medium and another one is the bulk modulus of the medium. So one tells you about the rigidity or stiffness of the medium. And the other hand, density, you all know that how much is the mass with respect to volume and how denser the medium is all about. So here's a tricky question. Will the speed of sound be higher in a steel block or okay, so let's do one thing. Let's go from base. So you all know what bulk modulus is about. It's about rigidity, stiffness, how fast, yeah, rigidity, stiffness, how rigid a structure is all about, how denser a structure is about. Okay, so what do you think is more rigid here? A steel or a rubber band? That's like a quick giveaway, but yeah.
Yeah, I mean, steel.
Yeah, steel is more rigid if we directly talk in terms. Right. Now, what is more elastic? Steel or rubber
Rubber.
band?
Rubber, obviously.
But rubber will break after time.
Ah, yes.
So it would be plasticized after some time. So it's not anymore elastic. So it seems out that steel is both more rigid, more elastic with respect to a rubber band. Now, why so? Because of the speed of sound in that medium. So here our speed of sound is like dependent as bulk modulus by density. Someone has something to say? It's not. Okay. Like this. And bulk modulus is nothing but also inverse of compressibility. So here the kappa is nothing but compressibility of the medium. Okay. So hence, wherever you look at if you have a rigid, denser medium, sorry, not a denser medium, if you have a rigid or a stiffer material, speed of sound will propagate faster in it. Or if you have a denser medium, you'll have more inertial mass to it. So then speed of sound will be slower in that particular medium. So that's how you'll always have to see the relation for it. But either case is always it is higher in solids, then in liquids, then in gases because of this relationship. So hence, if you let's say if you heat air, what happens when you heat air? The density there decreases. So that is why speed of sound is like it propagates faster in hot air, hot medium with respect to that. They are like slower in colder mediums. Okay. And then we had like this Doppler ultrasound mode where you see that, okay, at what region of point does the speed of sound traveling changes the velocity of the medium of a particle from one motion to from one position to another position. And from there you have like this three modes of Doppler. One is color Doppler, which gives you a tendency that if the blood or the particles inside it are moving towards the transducer, towards this sensing element, or far away from it. So the ones which are moving close to it are presented by red, and the ones which are moving away from it are like blue. So this is like opposite to how it's being done in astronomy. So there's an opposite convention, and this convention was whole solely taken because it is easier for clinicians to follow it through. Okay, then you have power Doppler. Now power Doppler is something which is like, now when you have color Doppler, right, it will only tell you about the direction of the blood flow. However, it won't tell you what's the maximum intensity there, or where your blood was higher, where it was slower. And nowadays, you can always see that where your blood is flowing slowly, sorry, not slowly, but where it's like it's going through at casual points, or it is like more rushing it off at through organs, like for example, your heart. But you might know where it's very slower. So to detect this parts or organs where it's you have a literally very slow flow, something as of your veins, it's very difficult to detect them. And from there only some specific diseases as aneurysm, or you have like atherosclerosis, those all comes into play. So hence you need to have some modalities as power ultrasound, power Doppler ultrasound, which will tell you about the intensity of the blood flow at that particular point. So this type of imaging mode is very sensitive to slow flow modalities, or slow flow tissue organs wherever you want to see through them. So it tells you about the intensity of the blood flow. And then the other one you have is spectral Doppler. So through this spectral Doppler, it works in conjunction with that of color Doppler ultrasound, but in this case, it will tell you about the direction along with its nature of the motion. Okay, so here, since we already had in tech, like nowadays, your clinical systems do have that. Okay, it will show you red and blue, but previously they weren't showing those nature, and you'll only get like sounds through the machine, and that's like doosh, doosh, like blood rushing in a particular artery or a vein. So in that point, what they used to do is like they'll correlate this sound of higher movement from one region to another region to a positive or negative part of the axis. So that's how they'll relate it, that if it's moving closer it or away from it. So how it went is like this first came, then this came, and then this came. Okay. So just so we saw everything about ultrasound and how it is in clinics, we'll just see something about how this now waves are being radiated. Okay, how it follows a principle there. So now let's say if you have, so this is like later, but if you have a what do you say, if I have a transducer right here, at points when it is emanating waves in this direction, those would be spherical. So the waves which come through ultrasound, or these waves are being called as spherical waveforms, and after a point when they travel a distance, they all become parallel to the axis that you're imaging at. So they are nothing but planar. So the regions which are near to you are more of called as into a Fresnel zone. So you can either call it as Fresnel, or but the literal pronunciation is Fresnel. And then later where you have this planar assumption, that is nothing but Fraunhofer zone. Okay. Now in Fraunhofer zone, you have planar fields, whereas in Fresnel zone, you have spherical fields. Why so? When a point source is emanating spherical waves, when these waves reach to a distance which is can be called as like achieving a actual position where it reaches infinity, at that point of time all are like assumed to be planar waves, and you don't have any losses there. Now in terms of losses, what I'm talking about is, because whenever these waves are being directly starting to emanate from this your sensing element, they'll have a simultaneous amount of constructive and destructive interferences there. And when these interferences start in an order that you no longer have destructive interferences, you always have planar fields there. And in this case, you don't have any losses due to diffraction. Okay, so diffraction contributes to more of loss of your energy, and that will also take up much of the useful information what your tissue was contributing towards you. So we never image whenever we are in the Fresnel zone. We'll always do and complete our approximations within the Fraunhofer zone. So, there are some approximations to it also, and the field there is also somehow called as, sorry, something where you look into the depth of field. So if you have gone through the week once, like fifth or sixth lecture about optical and contrast microscopy, so there the prof talks about depth of focus imaging. So that is nothing but your this one. So both this beam physics, laser physics, photoelectric physics, sound physics all follow similar physics in the case that you no longer have diffraction losses in that particular plane. So hence you have spherical to planar field assumptions. And here it's how there's like how the field strengths are being designed and what are the zones there. So both are from optics. Not all necessary to remember this formulas. It's just for your basic details how it comes through there. Okay. Then you had this beam forming. Now, what is beam forming? So we looked at here that you had a array of transducer, right? So let's just say, let's just make a transducer here, okay? So you are sending it from the first element, then you are receiving it back, again sending it, then you are receiving it back, again sending it, receiving it back. To make a complete image, if you do this one by one, one by one, one by one, your resolution is very poor. You won't be able to reconstruct the entire image in a form that you are correlating each pixel towards your tissue scattering or one on the order of your cellular scattering. Okay. So what people do is like this is something based on hardware complexity, and beamforming is something that you do on software. Okay. So how they do it to change it is that they'll send it using one element. However, they'll receive it using a group of elements, and that group of elements can be on the order of two. Okay. Again, they'll shift the aperture using another element and again group in using this. But this method also after a point didn't work out, and the SNR was being also lost when you were trying to image a deeper organs. Then what they did is they thought, let's just image it using a group of elements and receive it from the entire array. So when they did this particular part, now here when you see that when you are sending using all elements, receiving using all. So here, in this case, the energy that you get from this particular part of your region where the energy was being sent would be higher, right? Whereas the other ones aren't being emanated, but instead you are receiving from all elements. So in this case, you are nothing but patching all the regions, moving the aperture, patching it up, moving the aperture, patching it up. So the amount of energy where the time it took from one this particular, so here I was trying to focus an image, right, on the first order when I was doing. So that amount of time it took the farthest element right here on the aperture to receive the signal, and the amount of time this took, amount of time this took is nothing but which is called as beamforming. So this is nothing but spatial beam aligning. So you align each and every beam in spatial domain, so in your X and Y axis, so that you can get all pixels coherently how they were coming from the your tissue, how they were being scattered from the tissue. So it's nothing but you want all to be in the same phase. And there's like a basic, very preliminary order of beam forming, which is called as delay and sum. Now, what happens in there is, now you know that when you were trying to send the signal from one particular element, of course, it will reach back to this element very firstly, but it won't reach on the similar time scale to this element. So now you'll have to add some delay to this element so that all of the signal reach to our sensing elements at the same time. Okay, and then towards the end, you sum up all of them. So that is like basics into beamforming and how do you receive signals back from your tissue organs. Were you guys able to solve these formulas? What are written in here? If not, we can write as like solve them now. If yes, then we can move ahead. As like, is this geometry clear to you? Or do you want me to solve it?
I think it's clear.
It's clear?
Yeah.
Okay, so if for others who don't know, this is nothing, and I'll also add it on the extra notes, so where you can see on the lecture slides, where the content is being uploaded in that Excel sheet, you'll get this OneDrive folder link. So there it would be uploaded. So you can consider this as the focal point for where you want to image it, and this is the distance that you need to calculate it. So everything here follows your Pythagoras theorem as well as Euclidean distance. Okay, so just try like take axes and coordinates. One can be like cos theta component, the other would be like your sine theta component. And try taking mapping directions is like mapping projections there. Try seeing the distance which is there. It is following from this xi and this zf points. Try taking the Euclidean distance, and this is nothing but distance by time when it was maximum. So here now we are asking the x-axis to go from negative xi to positive xi. Sorry, xi. So when you go from negative to positive, instead here when you add that negative sign to it, hence this all becomes positive in this case. Okay. So if not, you can also go into those slides and I have like solved for the distance there. Okay. So that was all about ultrasound. Any questions here? If not, we'll go into texture then. So now you saw, like on the first week, we saw different MRI images. Then later today, we saw different ultrasound images. What you see, if you image a tissue using two different modalities, the scattering there changes, how that particular instrument is being performed, and the principles, the basics behind it, everything are different. So images that you get all are essentially different. So in this case, like this was a very nice example, and hence I like directly took screenshot of the slide here. So if you do have an image of liver here, and now you see the top two images of the liver are from MRI, whereas the bottom two are from ultrasound. So if you see in terms of MR, how the structure differences is like are there, where you have like image the liver parenchyma, and it's different from that of an external tissue. Whereas in case of ultrasound, you do see that this liver parenchyma does not have much of the tissue changes or texture changes. Your tissue scattering is much more similar with respect to that of your external tissue. So now the texture, what is texture? Texture is something local variation in intensity due to your tissue heterogeneity. Wherever your tissue has different heterogeneity levels, whereas noise is something which is uncertain, and that is due to your imaging sensing instrument which you are trying to use here. Now all of this imaging modalities will conventionally give you gray scale images, right? So that is how you everything you have gray, in gray levels, in gray color. It's not that if you change the color bar you can get it, but that's how conventionally people have been using it, and that's how it is easy for the clinical instruments to be used up on that level. Or else you'll need, if you need to render it on color, you'll need much more higher and complex hardware there. So hence they don't prefer it to do it that way. And how they differentiate it with is nothing but different levels of echogenicities that you are getting in the image. So here you do see it, the echo is much more brighter. So now brightness and darkness in MRI, and that we all know till now, this is nothing but due to changes in the weighted images. So how relaxation time are there being changes, whereas in case of ultrasound is solely based on scattering. So your scattering would be higher, lesser, echogenicity would be higher and lesser. So that is because of different echogenicities that you are looking at there. In ultrasound you do have some regions where you have like hypoechoic, you have hyperechoic, you have anechoic. So you have different regions here. So these are like some in cases if you have fluid filled cyst, or you have something as a solid tissue or tumor, you have something as a stone or a bone in between. So you'll get different regions there, and that's how your scattering will also differ. So in which case, which type of texture, which type of nature of a texture you should look at based on the is depends it is dependent on the modality of imaging also. So here the texture is being split into two. One is like structural and second is statistical. So both are like differentiated as this. So this is like very so if you get a time, go and look at this book that is Prince and Links, or till now you might have heard about it also. So in that book you don't have this information about this one, but you'll get in much more detailed information about the imaging modalities that you want to learn at, and you'll also have some basics of image level processing based techniques, which are like the ones which are listed here. Some more information about image processing, as you have those different filters as smoothing filters, Sobel filter, edge detectors, and those things. You'll also get those in this book. And there was one different book, I'll also tell it to you later. But also the book that Prof has mentioned also has this all things like given there nicely. So free PDF for that book is also available if you directly Google it online. Okay, so there are like this different patterns. I won't discuss them in detail because like these are very conventional techniques now, and nowadays no longer people use it. However, statistical based methods are being used. So we'll just go through them. Like I haven't included text about it, but I'll just say it briefly here. In this case, what happens is you have local binary patterns in your image. So you take a clockwise encoder and you look at each pixel and its neighborhood. Now, based on this particular neighborhood, you'll have a segmentation threshold there. Now, what the threshold follows as, you have you'll give it a value of 1 if the pixel intensity is higher with respect to the centermost pixel, whereas it would be 0 otherwise for other cases. Okay, so that's how the threshold follows for this. Now this type of cases, it was somehow in initially it was limited to cases like pixels or images of matrices of 5 cross 5 or something, but nowadays you know that 2D images are like 128 128 or 2056 to 2056, so they all vary in those manners. So hence there have been efforts by people who work core into image processing to solve it though, but to make it faster, because this one is faster because when we do so, we are nothing but making a binary map. So you don't no longer need to update the hardware to a point and you can directly use it through. But again, this type of approach, you can also make it rotation independent. So that's also better because if you change your image, your texture changes, right? And that is how people try and augment the data. So how they'll do is like if they are lacking on the data, they try and give like certain rotations or angle of degrees to your data. So they'll try and move your data images that you have and particular axes in a way that you are augmenting your data, and further for analysis you get enough data, so your sample size is also higher there. So hence this type of method, when you do like local binary patterns, they are like rotation independent when you want to integrate them in the future. So they always take a minimum bias there, so you do not need to be dependent on it. The other one which follows is nothing but this based on Fourier coefficients. So now you all might have learned about fast Fourier transform or discrete Fourier transform, or then you have like short time Fourier transform. So they are like you do Fourier transform across one particular window, average it, them patch it through all different windows, take those coefficients as like you have in Fourier transform as this AKBK coefficients, take those coefficients, see the maximum number of feature differences at one particular patch and the other patch. So this is something as frequency selective method. Okay, but in this case, this is like a bit more towards hardware complexity, because the order that you need to do Fourier transform varies as like n square, or sometimes people have made efforts to reduce it through, but it's also dependent on log approaches as n by log n kind of complexities of order, but it does take more time, hence the complexity is also higher in those natures. But yeah, of course, if you know this, you can also do wavelet based composition. Is nothing but you take spectral nature of your data and there you decompose it in between series of sine and cosine, and take your different patches of the image and relate one patch to another patch and how it's being differing there. So that's totally based on structure, and for that you need to have some prior information about the tissue anatomy that you're looking at. Okay. The other one is statistical. For this one, you don't need to know about the data that you are looking into, but it is something as you have this methods as co-occurrence and histogram here. So what co-occurrence mean is where two same values exist at a time. So what do you do is like now statistical based approaches are always based on joint probability. Okay, so joint probability of two different functions or features that we are looking at, both trying to exist at the same time. So here one such is co-occurrence matrix and second is like orientation histogram. So through one you can take like energy, entropy, you have like contrast of them. Whereas orientation histogram is like you map the histogram and then see how the maximum energy of the histogram is being changed from one form to another form. If you rotate it, then how it's changing. So it's like that. So that's all into this methods. Yeah, of course, statistical based methods also have something more into it, but that's focused only on MR or either only on what do you say, ultrasound based modalities. These are no longer being played into for X-ray or CT, which follows like simple back projection based algorithms. These are more for this volumetric or pixel based analysis type of imaging modalities. But what now here that we are looking at as is it's like very basic fundamental basis of how a texture in an image can be classified through its structural and statistical methods. Okay. Then you have segmentation. So yeah, of course, you all know more than me also that what segmentation and how segmentation nowadays is also being applied. So yeah, if you have like if different organs, not organs, different objects here. So based on the nature, similar characteristics or similar pixels there, you can take one as one object, label it, mark it as. Then that's how you do segmentation. You make mask of it, you take that mask, see it to another image, compare it with another image, try and see that if you're trying to, if you can segment it through, if you have a, like, let's say you have a traffic based data set, or if, let's say, if you have tumor in your organ. So you try and see if that one particular pathology, or not the pathology, if that type of mask is being matched, and thereafter it will like scan it through, give you cross-sectional images. In case of MRI, if you see, you'll get different slices, compare that through all the slices. If you don't get, you don't have, then you go into much more smaller local variations there and you see it. So that's how segmentation works. This is like simple blockchain processing for segmentation. So one way is like you can either do layer by layer, that's how MR based people do. Other way is like you do block based segmentation, that's how ultrasound based people do. Block based MR people also do, but how they do it is like they'll take one entire image as one block. Hence, that increases their processing time. Instead, in ultrasound, your data is much more smaller, and the data size that you get, which is being rendered into the systems, is also very lesser with respect to that of MR. Because, of course, you have one as 2D image, one as your cross-sectional 3D image. So, there would be this differences there. Okay, so one is like you grow the region, merge the region, you cut the region. So everything here is based on pixel similarities. If one you take one pixel only of one distinct region, you compare it with all regions. If you say similarities, group them into one region. Other similarities, take it apart, leave it other. Then you have like edge based. So these are like some similar filters you might have studied prefers, like Robert, Privet based, Sobel, Canny. These are like edge detectors. These are like high pass, low pass based variations. These are like cross based, logarithmic based. So these are different filters there. So this kind of methods we no longer use nowadays, because here it's like it will only work if you have smaller matrices. It won't work as so you'll have to do some as a frequency domain based filtering, and then later come back into spatial domain and do it other ways. Okay, then you have thresholding, global thresholding, local thresholding within a patch or within the entire image itself. You have clustering. Clustering can be semi-supervised or supervised. K-means here is both semi-supervised and unsupervised. So you can look at it. It is based on centroid-based classification. So it is mainly used for classification. Fuzzy C-means is also for that. Then here, then you go into your entropy-based methods, learning-based networks. So those are the other forms of block-based segmentations you look. Okay. These are some examples here. So for region based, you always need to have a seed. For edge based, you always need to have a hinge point there. For thresholding, you always need to consider if you have equal amount of intensities from one place to another, or else this type of techniques always make your classification or your segregation based method to be too much biased. If you don't know that, it would be biased on the user and you won't be able to use it for other techniques. Okay. Here I've shown for basic simple clustering. So how clustering people previously used to do is that they'll make a classification layer, or they'll make a decision layer around that corner, and they'll see how the centroid of each of the classification groups that you're looking at have been separated. If they are separating close enough to each other, then they are in like one part of the decision layer and the other part of the decision layer. Okay, if not, then they look it at and segregate it differently. So after clustering, they are like all different four of them because their centroids were like in between them.
But in a similar case now, you have something newer, is not newer, but how they have been done. So this is a similar form fashion that you have been doing till now, discriminative based classification, where you see that, okay, my centroid for this model is lying here, centroid for this model is lying around here. So I'll have a decision boundary, and I do know that the objects which are like on the other half of the layer and other half of the layer are totally different from each other. So I can just classify them or label them as different objects there. Whereas if you have something as generative, it won't only try and differentiate it, but it will also make new classes there and saying that this one is not only dog, but it is some another species of dog which looks like this one. So it will help you differentiate there. So one is based on joint probability, another is based on sorry, cumulative one. Okay, so here this will try and cluster based on similarities. Your k-means is something as discriminative model, your hierarchical clustering, where a generative based on learning is nothing but if you have something as autoencoders and those. So if you generate models to describe different clusters and use them to classify the points, so you can also have different Gaussian mixture models, that is something as encoders, or if you have different generative learner models, so you can do using them. Okay, so that's all about this lecture. If you have further questions, do let me know. I haven't covered the last two ones, so I'll cover it later because the assignments also don't have any much more information into it. So we can directly go into assignment, or else if you have any questions, do let me know. I'll also take a 2 minute break and give myself some time to speak. Let me know if you have any questions in between. No questions? I guess we can go to assignment then. I hope I'll get answers from you. Okay. So the first question, I guess you can see. In order to achieve segmentation of multiple regions through region growing, which of the following can be used? How do you do it? As like one pixel a distant region, or multiple pixels a seed for only one region, one pixel as multiple region and no seeds. Sorry. Hmm? Do we have people in here? Okay, so each and every time you only need one distinct seed. Okay, so you can mark one pixel as one distinct region, and since you are using this region growing method, so based on the different similarity, distinct features there, it will grow your region, and hence will be able to do your segmentation. So one region, one pixel as one distinct region there. Okay, then next one. So this is something as area under the curve analysis. So if which one do you think gives you a better performance? So higher it is, the better it is. So which one? Which of the following values is like suggests that your area under the curve will indicate a better performance?
0.9.
Yeah, yes, of course, zero point 0.9. So zero point 0.9 is nothing but it will show you a better performance there. Okay. Then this one. So there were two coefficients, and these are like more of for segmentation based techniques only. The dice one and Jaccard coefficient. So one is like here. This one is like your intersection of, let's say, two quantities A and B by union of both of them. Whereas the dice coefficient on the other hand is like two times of intersection by the total of the quantities, if I remember it correctly. So what do you think is the relationship in between dice and Jaccard coefficient here? Of course, this is magnitude.
It is also option B. J equal to J.
Which one?
J equal to Judy.
This one. No, but you do see this here. So because of that, this is this option. D is equals to 2J by J plus 1. So if you insert this one and this one, also if you do the other way around, you have it as, I did it the other way. You'll get one as this one, the other one would be D by 2 minus D. Okay.
Okay.
So that's like B option there. Yeah. Now this one. In random walks for segmentation, so random walks is again that if you select one, move from one heterogeneous cloud to another cloud, then map the labels there. So based on, so for if for one pixel you have a label, for that label you have one probability. So nth is nth like that. Then so the number, oh, that's the question only. Okay. So number of label probability maps is what? Is it less than the number of labels, equal to it, more than it, or twice it?
It's more the number of labels.
It's equal to the number of labels. Okay. So that does mean that for each pixel, you have a label, and for that label, you assign a probability to it. So it's always that nth pixels, you have nth labels to it. So it's always equal to number of labels, hence the number of probability maps. Okay. Okay, here. So in an active contour, so contour is nothing but the region around which you are segmenting it at, which points update their positions iteratively. So you have 2 points there. One are like hinge points and non-hinge points. So which points can move freely if you have an active contour? So here you can only move your non-hinge points because the hinge points would be actively there in your segmentation mask. You won't be able to move them, but the non-hinge points can be moved iteratively because they are the ones through which you are analyzing your region into. Okay, so that's again option B. And here, which of the following does the cost function in active contour model will be taken into consideration? So which ones do you try to minimize where you have an active contour, internal and external energy? Which one? Are like both of them or neither of them? So I know I didn't teach this part, but this is like more of image segmentations and also that's there into last 3 lectures also. If you don't get it now also, you can go and look at the slides again. But these questions are more of similar to your current assignment. So that's why I thought let's just discuss it and so that you'll get a glimpse of an answer also and how it should be solved if there are any numerical questions below. So for this question, the answer is like you both always you need to consider both of them. So if both are minimized, then only you'll be able to achieve your cost functions in a optimized way. Okay. In an active contour, which of the following are required for convergence? So of course, whenever you're doing it, if you're trying to minimize both of them, you need both of them to be minimized also to achieve a convergence there. Okay. D, huh? Then you have a balloon model in an active contour, which has an external force, which is a weighted function of what? So again, since now we were looking at energies, so it is again a nature of both the force, which is inserted due to the internal energy, and the external energy itself. So same question is being asked in multiple fashion here again and again. So this is one such question that you all can solve. Given the pixels, you have A, B, C, D, and you have a seed S in an image. Identify the pixel which is nearest to the seed, that is RGB in terms of colors that you have been given. A is this, B, C, and D, and you also have seed for S. Use Euclidean distance to measure color distance. So now we want to do, you need to find a pixel which is nearest to the seed. That means you need to see where it is minimum. Okay, so where from, from S for this A, B, C, D, which of the distance for them, DA, DB, DC, and DD is minimum here. So directly do is like square root of one coordinate minus the other coordinate whole square, second coordinate, other coordinate, like that. Euclidean distance, and compute it. Which is the one which is closest? You all can do this, right? Like doing this Euclidean distances is also there in further questions. You don't want to do, we can skip them, but eventually you'll have to do it. So just to boost up your confidence so that the assignments that you do have a correct answer, you can try them now. So we can solve it also if you need. So yeah, so how you do is that your seed minus your, let's say, any coordinate whole square plus your seed minus other y square plus your seed minus z whole square. You see the distance for all, from A to S, for B to S, C to S, and D to S. So if you do for all, uh, okay. The answer here in this case is D probably. D or C mostly, because you have this is 1, 2, 3, it's more further up. B is also further. You have 4, 5, 1, 3, 5, and 2.
These
The rest,
dancing.
yeah, so C would be the answer there. C is the answer. Okay. Now, when you look for, so when you do this area under the curve analysis, or when you look at and sensitivity, specificity, those things, you have something as precision, you have something as accuracy. You represent them in terms of the matrices which are called as true positives, false positives, true negatives, false negatives. So there's a matrix for it where you call it as specificity, where you do it as accuracy, precision, then you have something as recall and F score, something like that. So for precision here, if you don't remember, the formula is like true positive. So precision is like always right. And then it is followed by like ratio of all positives. So the answer for that is B here. Okay. Now here also similar question. So like here I won't ask you to calculate it now again, but what you need to do in this case, I'll just tell you. Find the class label, this WI, for the pixels which are bearing the corresponding RGB values. So you have A, B, C, and D given, and the values of the color in RGB for the two seeds are given to you. Okay. Now in this case, what you need to do is like now you know for A, B, C, and D what values have been given to you. Then you know for W1 and W2. So now you calculate the distance for all in between W1, sorry, for all this labels from this W1 and W2, the distance for minimum. So where it is minimum as a function of A and this class W that you are comparing it with. So not A, but here like, yeah, of course, now you understand, right? It can be either A, B, C, or D, okay? So wherever it is minimum, that particular class would be assigned it to. Okay, so let's just assume that for this, if I get something as 100, if this I get as 50, then this class would be W2. Okay, so that's how I just gave you an example, but that's how you need to calculate. So you need to compute a distance from this and this and this and this, see where the distance is minimum and assign it as the class here. Okay, so for this question, the answer would be A. Okay. Then next, which of the following are the advantages of a retrospective experiments over prospective experiments? Now, do you know what retrospective and prospective experiments are? One which you do like in the current, or which you have data from the beginning and that something which exists. And prospective is something which is longitudinal. You'll change, the variables will change with respect to time. You'll look it as in how you go into the future. Okay. So which of the following is true? Is it less expensive, free of cost, and something about class balance? I don't know what about class balance, but yeah. So yeah, of course, this retrospective experiments are like less expensive and they are generally free of cost. And so that's only option A, that one that you'll be looking at. Okay. So here the answer is A. Samples of a data set should ideally be what? So if you have a big data set, you'll always feel that the samples or the data that you're getting are not biased, of course. So the biased ones are always crossed out here and they have a higher degree of variation. So it need not to be that always you have a lesser variation. So it might also be very like wrong in that case. So low variance does not essentially mean lower standard deviation. So it would be wrong to consider that. But you always say that it should be unbiased and of higher variance. Okay. So that's answer A. This is a nice one, but I won't want you to calculate it though here. You'll need to write multiple matrices for it. So what we can do is, I'll just tell you how to do it because you'll have to solve for another assignment question also. You can just cross-check the answers then. Okay. So what's the question here? Which of the following represents the co-occurrence matrix? So that is nothing but where you have similar pixels attaining at same time of a 2-bit image given below. An app operator d equals to 1 and a direction this. So any is nothing but northeast direction is being employed here. So on the positive one. So out of the options, do always see that if you are taking a current, sorry, someone joined. If you're looking at a current versus northeast option, or you're looking as a northeast direction versus current. If you don't have the answer that you're looking at, try taking a transpose of it and see within the options that you're looking at. Okay. Now to solve it, how to solve this type of question. Okay. Where did I solve it? Yeah. So in this case, we see that this is a 4x4 given matrix. Okay. And the values of the pixel, since it's like 2-bit, so the values would be like maximum 2 raised to 2, that's 4. So 0, 1, 2, and 3, right? And the gray level occurrence matrix is 4 times 4. So how many pairs that you will have? You will have like row minus 1 times column minus 1 pairs. So those would be like 3 times 3. So you'll have something as 9 total pairs. Okay, and out of these 9 total pairs, you'll have to see which one are the valid northeast neighbors. Now, to calculate the valid northeast labels, what you'll do is, so you'll start from the list of rows for each one of the rows. So now you'll start, let's say, for row 2, row 3, row 4, you'll compute the number of equal pairs that you'll have. Okay. Now for those pairs, you'll compute the minimum distance there. After computing the minimum distance, so first is your pair for each row, a pair that you're looking at, okay? And then the minimum distance from this any region pairs that you have. When you get that, you see the occurrence, how much occurrence you have for one region. So let's say if this row would start, you have like, let's say for, so how this is, second row and the first column has something as 0. Okay. Now if you have something as 0, now for your northeast and 1, so this one, which one? For your northeast, and if you are looking it as, let's say 1 comma 2, you have here as 3 here. Okay. So this both are then clubbed as 0 comma 3 here. Then you further go and go on, go on. It's like you take gradients of them, again go, again go, again go. Then you compare both of them. How many times the occurrence do you have? Based on that, you'll get a matrix. If you don't see the answer here, try taking a transpose of it. Okay. Just try solving it. Solution will be posted there. So you can directly also see the solution if you don't understand what we just discussed now. And the answer for this one, I hope, was C. Yeah. Answer for this one is the C one. I remember this answer because when I tried solving it, I wasn't getting the right answer. Then I tried transposing it, so it came. So they have not written what convention they are here following. So if not, then you can directly do it this way. Okay. This is bit tricky, or let's say not at all needed, won't be used anywhere else. So I do think so shouldn't be asked in exam. But if it is, then do remember how you should solve questions like this. Okay. This is simple. Now you have want to compute specificity here. So what is specificity about? So for the first
C.
one, if you want, sorry, yeah, yes, 7 seconds.
Yeah, yeah, C, I guess. True negatives
Yeah,
and
it's about negatives with respect to your negatives and positives ratio. So for this one, previous one, you can always go and look your lecture 11 slide. So there you'll have, sorry, not lecture 11, but slide 11 of your lecture on like texture. That particular slide has this thing. Okay. Yeah, this is done. Then you have your like when you plot this ROC, you do this receiver operative characteristics for classification. Which of the following do you get? You get specificity, accuracy, precision, the sensitivity, F score, and what?
D.
You always get this ones, right? Sensitivity and specificity. And you have
Okay.
like different ratios of true negatives, positives, and those points. From there, you can calculate F score, precision, accuracy, and there's also one more thing that's called as recall. So this all four are different, but this ROC curve gives you about this two analysis. Yeah, sensitivity is how close and how many true positives you have in your classification model, whereas specificity is how minimum your true negatives are there inside your model. So specificity can also be one in cases that is 100% specificity. That doesn't mean that your model is like totally wrong. That does mean that your model has identified true negatives as all true negatives and false positives as all false positives. Okay.
One more thing, I just have one doubt. Uh, in one of the slides or the lecture, the prof mentioned something, the area under ROC curve.
Hmm.
Can you please tell what is area under ROC curve? Like it depicts sensitivity or the specificity of the characteristics?
Both.
Okay, both. So, I mean,
Yeah.
the greater the area under ROC, the greater will be specificity and sensitivity both.
So specificity has a trick here because it depends how you are looking it at, but sensitivity will always be higher.
So we can directly link area under ROC to specific sensitivity. Sorry.
Sensitivity. Yes.
Okay. Okay.
Then this is the one while segmenting an image into two disjoint regions. So if you know your probability, disjoint regions are the ones which are like mutually exclusive also. So you have two regions here. Identify which of the following relation is true. If you take union of both of them, you get entire image, intersection entire image, union null, or intersection null. Which of the following?
A.
Yes. 1, 4 and not 2, 3. So these are like if you take union of both regions, you'll get the entire image. And if you take this intersection of both of them, you'll get nothing, null. Because they aren't intersecting at any point. They are mutually exclusive. Okay. So if you have a retrospective data, which one of the following falls here? Is it an epidemic data or imaging modality efficacy based studies? So in either of the points, if you see epidemic data is always available because it was an epidemic at some point. So that happened. So that is something as retrospective data collection. Retro is like something which happened already or it is like being done now, not prospective, not from t equals to 0 now. And then imaging modality efficacy studies. So efficacy studies is like something that they already know that was trying to see if it would be efficient or would be done. So in this case, it would be which answer then?
Both.
Both options. Then this one question. Hmm. So this one is also similar that how did we did that gray level occurrence matrices. So it is based on that local binary pixels. And here you need to compute the value. So here you'll do something as those binary pixel masses. You'll see get masses for one range of values to the center pixel, another range to the center pixel, another range, and then you make this matrix there or a vector there and try moving the vector in clockwise fashion that we saw that try encoding it like this. In that point, you'll get the circular shifts, the lowest shift occurrence, that would be your answer. So for this one also, you'll have to do some multiple occurrences and then eventually you do it as like, let's say 8-bit comparison or a 10-bit comparison. That will get your answer to be as 119 in this case. Okay. Last one, which of the following is an example of graph-based methods for image processing? Region growing, random walks, convolution, cropping, not at all cropping. Then region walks is also not possible. Convolution or random walks.
Random walks.
Yeah, of course, because there you're essentially trying to get pixels within similar features and then trying to differentiate them, whereas the others are more of selective based methods, and this is growing as segmentation based method. Okay, so we are done with this week. If you have any further questions, you can stay back and ask me. Or else, thank you for joining. Any questions? Okay,
No, no. Thank you so much.
thank you so much. Thank you for joining.